Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And in this video, we're going to prove that this conceptual function here, which is 0 whenever you plug in a rational number and x squared when you plug in an irrational number, we're going to prove that that function is continuous at 0. It's actually not continuous anywhere else, but at 0. This is a function I often introduce in my first year calculus class because it's a great theoretical example. And let's go ahead and start by graphing this just to get an idea of what it looks like. So every time that we plug in a rational number, and I'll do this maybe in red, the output is going to be 0. So there are an infinite number of rational numbers. And if you think of numbers between, let's say, -1 and 1, which I'll mark on here, -1 and 1, which are rational actually because they're ratios of integers, any number between -1 and 1, including -1 and 1, many numbers I should say, an infinite number of numbers between -1 and 1 are rational. So therefore you have an infinite number of points between -1 and 1 whose output for this function, whose y value, will be 0. Yet there are also, between any two rational numbers, an infinite number of irrational numbers. And so if you can imagine, if I were to just want to graph y equals x squared itself, it would look like a parabola. Well, that's what we're going to get, except the parabola will have a bunch of little holes in it, right? So it looks something like this. It's so dense, honestly, that you wouldn't be able to tell if somebody actually tried to accurately draw it. You wouldn't be able to tell the difference between a true parabola and this graph here. You wouldn't be able to tell the difference between the true parabola and what that person was graphing, that is. So everything in blue is where the irrational numbers, the y values for the irrational numbers, and everything in red would be the y values for the inputted rational numbers. If you look at that, I had to lift my pen continuously, or all the time. I shouldn't use the word continuously in this example, but I had to lift my pen all the time to graph that function. However, that's what most people think is the definition of discontinuity. If you have to lift your pen continuously to, or all the time, to graph something, that must be discontinuous. That's actually not true. This is a great example of a function where, yes, you have to lift your pen all the time to graph anywhere, right? It keeps jumping between 0 and some number, right? The y values do. But it turns out that if you zoomed in enough around x equals 0 here, that the distance you're lifting your pen to graph the irrational outputs versus the outputs for the rational numbers, that distance gets smaller and smaller and smaller, and eventually that distance is pretty much nothing. It's infinitesimally small. So recall, to prove continuity, we need to prove that the limit as x approaches, well, in this case, we're trying to show continuity at 0, so as x approaches 0, we want to show that the limit as x approaches 0 of f of x will actually equal f of 0. That's what we want. And of course, 0 itself is a rational number, so it should return 0. That's what we want to prove. So let's go ahead and start the proof here. This is going to be an epsilon delta proof. And let's go ahead and remind ourselves of the epsilon delta proof. This limit implies that for any given epsilon greater than 0, we should be able to find a delta, usually based upon that epsilon, that's positive as well, such that whenever the distance between x and 0 is less than delta, or in other words, whenever x is within a delta neighborhood of 0, not including 0, it will imply that our function is within an epsilon neighborhood of the output 0 that we said should be the case. So that's what we want to prove here. Let's go ahead and do some scratch work first to kind of set up. And remember, with scratch work for epsilon delta proofs, you're really going backwards. You're assuming that you got to this point in your proof, And so you're assuming that you somehow proved it. You want to see how you got that done. You want to go backwards and see how you got that done. So the scratch work will look like this. And this is not what you show the world. This is just what you do so you can figure out how the proof works, which is a common tactic in mathematics. Is you want to prove something, and so you say, well, what if we got to the end result? What if I got to the proof? How could I work my way backwards to figure out how I got there? So let's assume, and it could be a bad assumption, that the distance between f of x and 0 is less than epsilon, which implies, by the way, that the absolute value of f of x is less than epsilon. The problem is f is a piecewise defined function, and so there are two cases. And so you need to kind of break it into those two cases. So if x is rational, because we're trying to find a delta neighborhood, so we know that we have an infinite number of values, x values, within this delta neighborhood. So I'm just saying, if x happens to be rational, then f of x has to be 0 by definition of the function f here. If f of x is rational, if x is rational, then f of x is 0. So what does that imply? It implies that the absolute value of our function, which now, when we're plugging in rationals, is just the absolute value of 0, which is 0 itself, must be less than epsilon. But that's given from the get-go. So remember, when you're going to prove this, you're going to assume that somebody's handed you a positive epsilon. This guy right here. So that is true. It is trivially true. So now, what do we do? Let me erase that. What about if one of our numbers within our delta neighborhood is irrational? Let me scroll down. Well then, f of x is equal to x squared. Again, by the definition of f of x. If x is irrational, we know that f of x is equal to this x squared right there. Great. So what does that imply? That the absolute value of our function, and the reason why I keep talking about the absolute value of our function is because of this statement right here. Assume that the distance between our function and 0 is less than epsilon, so it implies the absolute value of our function must be less than epsilon. So I'm really concerned about that. So if x is irrational, then we know our function is x squared, which means the absolute value of our function, which is the absolute value of x squared, is less than epsilon. And we can actually, at this point, solve for x squared. That implies that, take the square root of both sides, that the absolute value of x is less than the square root of epsilon. And that will actually be my choice for delta, for the size of the radius of my delta neighborhood. So visually, this means that, let me go ahead and zoom in a little bit. Visually, this means that I have found a neighborhood, a delta neighborhood. So this is 0 plus delta there, and here's 0 minus delta, such that as long as I let delta equal the square root of epsilon, all the x values in that highlighted delta neighborhood will lead to y values within the given epsilon neighborhood. And let me just draw in a given epsilon neighborhood here. So they've given me a plus minus epsilon around the height of 0, right? So here's 0 plus epsilon, and this is 0 minus epsilon. So that's really what we're saying. Getting back to normal size, let's go ahead and start the proof. I'll do the proof in black. Remember, when you do a proof, an epsilon delta proof, you take the language of the precise definition of a limit, and you just insert what you found your delta to be. So for any epsilon greater than 0, choose our delta neighborhood to be of size square root epsilon. So that's the radius of our delta neighborhood. Now, if x is really close to 0, how close? Within our delta neighborhood. That's what this is saying. Then the absolute value of x must be less than the square root of epsilon, because that's what we chose our delta to be. Now, how you proceed from this moment just depends on your choice of how you're going to do the proof. I'm actually just going to continue forward as if I'm doing a normal epsilon delta proof, and then make a mention of something at the end. So I'm going to square both sides right now. So this implies the absolute value of x squared is less than epsilon, which implies the absolute value of x squared minus 0 is less than epsilon. And now I'm going to make the mention, because that's not necessarily f of x, that's just one piece of f of x. That x squared right there, let me highlight it, is the value of f of x if x were irrational. Thus, if if x is irrational, then the distance between f of x and 0 is less than epsilon. On the other hand, if we happen to be handed an x value that's rational, well, the absolute value of f of x minus 0 is the same thing as saying I have the absolute value of 0 minus 0, because x is rational and f of x therefore is 0. And that is equal to 0, which is by definition less than epsilon. That is by assumption that's less than epsilon. And that assumption actually occurs right at the beginning. It's by definition actually right at the beginning. For all epsilon, that's positive. So in either case, our distance between our function and 0, whether x is irrational or rational, must be less than epsilon. Hence, the limit must be true. However, if you could tell by the way I've written this, that means that the limit as x approaches 0 of f of x is equal to f of 0, which implies f is continuous at 0. Such an interesting statement, and I should probably finish out the proof here. Such an interesting statement for an odd-looking function to say that this function right here, which has really an infinite number of discontinuities, everywhere there's a discontinuity, right? And yet at 0, there is not a discontinuity. It's actually continuous at 0, even though to graph it, no matter how much I zoom in, I keep having to lift my pen. So that conceptual idea that a function's continuous if you don't have to lift your pen to draw it, is a flawed definition of continuity of a function.